Hello everybody and welcome to yet another math video. In this video I will be going over Gauss-Jordan elimination, and this will involve me going over Gauss-Jordan elimination, just an overview again, and row operations review, and I will also then go over Gauss-Jordan elimination with more equations, like 3 equations will be the main focus for this video. Let's get to it. So if you've seen my video about matrix basics and Gaussian elimination on 2 equations and 2 variable systems, this slide might look familiar. So if you have not seen that, I will link the previous video below in the description so you can see that. But here, I'm just going to go over it very quickly. Gauss-Jordan elimination is a way to solve systems of equations using matrices. Here's the basic idea. We get an augmented matrix here, and we use lots of row operations, and we get lots of minor headaches, and we get to this augmented matrix here. What's special about this augmented matrix is that the principal diagonal has elements of 1. They're all equal to 1. And every other element to the left of this vertical bar, above and below the ones, are all zeros. That means it's in reduced row echelon form, which makes finding the solution very simple. Again, very quickly, the top row only has one variable in it. It's an x. It's 1x equals -2. So we knew that we would know the x value would be -2. The y value similarly would be 7. The z value similarly would be 13. All right, and again, we could write that as an ordered triple. I did not write this down in the last video, so we could write our answer something like this: -2, 7, 13. And the row operations are as follows. We can have a row swap, which allows us to switch the position of any 2 rows in a matrix. We can multiply a row by a scalar as long as it's not 0, and then replace that row by itself, by its new scaled self. And then we have what I call a row combination, which multiplies a row by a scalar and adds it to a different row, and that different row gets replaced by the result of all this stuff. That's the short overview, short review. Let's get into solving systems with 3 variables and 3 equations. Use Gauss-Jordan elimination to solve the system. So these systems that you'll see in the next 3 examples are bigger than the previous systems, as there are 3 equations and 3 variables. So the first thing you'll want to do still is make sure all of the variables are on the left side, all of the constants are on the right side of each equation. Make sure all of the variables are lined up correctly. Ta-da, they all are. Then we can start in with making the augmented matrix. And that isn't so bad. We have all of the coefficients, 2, 3, 1 in each column. So the first column would represent the x's, the second column would represent the y's, the third column would represent the z's, and this vertical bar here, it represents the equal signs, and then the constants are here. Pretty straightforward. So what I'm going to do now is try to get a 1 in the upper left hand corner, or in the first position here on the primary diagonal, which is called really the principal diagonal. So I need to get a 1 here, and there are plenty of ways to do it. The first thing we could do is we could just divide this entire row by 2. It won't create any fractions for us, and that's a good way to get a 1 in the upper left-hand corner. We could row swap here to get a 1 in the upper left-hand corner. This middle row, maybe you've noticed when it was in the matrix and not so much in the equation, but the middle row is divisible by 3, so maybe we could get a 1 here and then row swap it to the top. Any way you decide to get a 1 up there is going to be a good way to do it. So what I'm going to do is I'm just going to say, let's divide row 1 by 2, and then we can replace that back into row 1. So when we divide everything in row 1 by 2, we'll get 1, 2, -5, and 1. So the new matrix will look like this. And I realized that I missed a negative sign up here, so I made sure to include it. So -2 divided by +2 is -1, so the -1 in the top row now. All right, there's a 1 in the principal diagonal here. Here we go. Now we just need to get zeros underneath that 1. So we need a 0 here in row 2, and we need a 0 here in row 3. And the way to do that is by row combination. So I'm going to go ahead and do the 0 for row 2 first. And that will require the row 1 to be multiplied by something. We will add it to row 2, and then we will replace that new result in row 2. And it's very simple to see that we will need to multiply row 1 by -3. And again, it's so simple because that 1 allows us to just use the opposite number here. So we can take 1 times -3, add it to +3, and that will give us the 0. So what I will do is multiply everything in row 1 by -3, and I will get -3, -6, +15, and +3. In the new matrix that I will make off to the right here, I will leave row 1 alone because we're not replacing row 1 at all. And -1, I will leave row 3 alone because we're not doing anything with row 3. The only row that's being replaced right now is row 2. Oops. So what is row 2 going to get replaced with? Well, the first element in row 2 would be -3 plus 3 is 0, so let's put a 0 there. The next element would be -6 plus 9, which is 3, so we can put a 3 there. The next element is 15 plus a -21, which is a -6, okay? And the last element would be 3 plus 0 is 3. So there's the new row 2. So you can see we're working our way through getting zeros underneath this 1. So there we go. Now we just need to get this 1 down here into a 0. So we have to use row 1 again. So we will have row 1. There we go. Row 1 plus row 2, and plus row 3. And we will replace row 3 with that result. Now we will multiply row 1 by -1. So when you multiply row 1 by -1, you'll get -1, -2, +5, +1. And we can go ahead and add those two rows together. So in my new matrix that I'm going to be writing here, row 1 doesn't change, row 2 doesn't change, but row 3 will. So just element by element addition, -1 plus 1 is 0, -2 plus 5 is 3, 5 plus a -12 is 7, 1 plus 1 is 2. So the new row 3 looks like this: 0, 3, -7, and 2. All right, so we have our 1 here, and we have our zeros below. We're done with that column. That column is completely finished. Our next step is to get a 1 on the primary diagonal. So we need this value to be a 1. Now, in order for this to work, we have basically eliminated row 1 from being usable. So from here on out, we have to be using rows 2 and 3. Once we get this first column being 100, 1, 0, 0, we can only use rows 2 and 3 to figure the rest of this out. So we can either swap rows to get a 1. Well, we're not going to be able to get a 1 here because this row also has a 3. Or we can divide. And to get a 1, you just have to divide a row by whatever number is there. So this would be row 2 over 3 and then replace row 2. So when we divide row 2 by 3, we will get this matrix right here. And what I'm going to do is I will copy this matrix, and it'll be the first matrix on the next slide because we are clearly out of space. But the goal here then becomes, on the next slide, that we want to, we have our 1, we have our zeros below, is we want to, we got our 1, and we want to get a 0 below this 1. So let's go ahead and look at that on the next slide. As promised, here we go. We need to turn this 3 into a 0. So that will involve row 2 and row 3. Again, row 1 is done for now. We can't do anything else with row 1. So we have to use row 2 and row 3. So I know I will be multiplying -3 to row 2 and then adding it to row 3, and then row 3 will get replaced with all of this math that's going on here. So multiplying row 2 by 3 will give me -3 will give me 0, -3, 6, and -3. So we can add all of those together, element by element, and get this new matrix here. So this is that new matrix with all the math being done. Finally, you can sort of see that we're very, very close to getting our principal diagonal of all 1s. And we have zeros underneath the principal diagonal, which is very, very nice. The only thing we have to do to get the principal diagonal of being 1s is taking row 3 and dividing it by -1. And when we do that, we will replace the result, or place that new result in row 3. So now we have the principal diagonal, it's all 1s, and we have zeros underneath. The next steps, the next bit of row operations, we need to turn these top numbers above the diagonal into zeros as well. And how we do that is we start with the right side, the rightmost one in this diagonal, and start eliminating the numbers above it. So kind of like we started on the left side and got the zeros below, then we moved over and got zeros below, then we don't have any more zeros below. Now we have to start here and work our way backward. So I'm going to do a couple steps here at once. This will be row 3 plus row 2, and we will replace row 2. But we're going to multiply row 3 by 2 this time, because the opposite of -2 is +2. And simultaneously, I'm going to multiply row 3 by 5. So 5 times row 3 plus row 1, because that's where we want a 0, and the opposite of -5 is +5. And then we will replace row 1. So I'll get the matrix over here. So having done a little math here without actually writing it out, you can see we are super close to being in reduced row echelon form. We have the zeros below, we have the zeros above that last one. The only one we have to worry about now is this 2, and we can turn that into a 0 using row 2, right? We're moving backward. I used this one to get these zeros. Now I have to use this one to get this 0. And so we will just take row 2, we will add it to row 1, and replace row 1 with this new result. What do we multiply row 2 by? Well, seeing as how we're trying to get rid of a 2, we will multiply row 2 by -2. And when you do all of that, you'll get this matrix here, which then translates over into x equals -2, y equals 3, and z equals 1, which we can represent as an ordered triple, x, y, z. So again, depending upon how the answer is being asked, Normally, it is very traditional to give an ordered triple, but you could also list them out if it's asking you to do that. Let's take a look at another example. So here, another example, Gauss-Jordan elimination to solve the system. And you may notice a couple things right off the bat. The variables have changed to x sub 1, x sub 2, and x sub 3. And you may have also noticed that this bottom equation does not have an x sub 2 term. If you have any missing terms, you should absolutely fill them in with a 0 variable term. So this would be 0 x sub 2's in that final equation. And that is because when you end up writing a matrix out of this system of equations, you can't have any blank elements. You have to have a number or a variable or some expression in every space in a matrix. So that being said, the matrix would look like, all right, here is the resulting matrix from this system of equations. And I'm going to go through and solve this one slightly differently than what I did in the last example, just to give you a different way to see it. And if you'd like this new way of doing it, then feel free to use it. It's an absolutely valid way to do it. We still have to get a 1 in the upper right-hand corner first. Unfortunately, we can't just divide by 3. That'll create fractions in the matrix, and I'm just a big proponent of no fractions in a matrix. So if you can row swap, let's do that. It looks like we can row swap here, so this would be row 1 being swapped with row 2, which gives us the new matrix. There we go. So we have the 1 on the principal diagonal, and just like the last example, I mean, it's going to start out like the last example. I would like to get zeros beneath that 1. So in order to do that, I know I'm going to be taking row 1 and adding it to row 2, and we will place that result in row 2. But what will we be multiplying row 1 by? Again, it's as simple as what's the opposite of this number here. So we're going to be multiplying row 1 by -3. And I can do something very similar. We will multiply row 1 by -2. And we will add it to row 3. And we will replace the current row 3 that is there. So the new matrix will look something like this. Fantastic. So here's the new matrix. The next step, again, we want to make sure we get a 1 here in the next part of the principal diagonal. So we can either do one of two things. We can either row swap, I don't think that's going to do anything for us, or we can divide a row without creating fractions. We should be able to, I guess it's this one here. We can divide this row by whatever number we're trying to make a 1. So we're trying to make this 2 into a 1, so we can divide this whole row by 2. It'll be row 2 divided by 2, and we will place that new result into row 2. All right, so again, you can see when we divide, we have our 1s on the diagonal. We are continuing that trend. We have our 0s below the first one. But instead of only finding the 0 below this next one, I'm also going to find a 0 above it, which allows me then to use 2-row operations like I've been converting over to. So I'm going to multiply row 2 by something and add it to row 3. And we will place that new result in row 3. But I will multiply that row 2 by a positive 2 because that is what is the opposite of the number we're trying to turn into a 0. Similarly, I can multiply row 2 by -1 and add it to row 1, and then we will place that result in row 1. So let's see what this new matrix will look like. There we go. This will be the new matrix after these row operations. And I'm out of space, so I'm going to make sure that this matrix appears on the next slide and we can continue down our path. All right, here we go. We are continuing down our path to the goal of getting ones on the principal diagonal and zeros everywhere else. So the final step here would be to get a 1, the last one on the principal diagonal. Again, we always want to be doing that first. We need to get the ones because it makes getting the zeros much easier. So I need to turn this 5 into a 1. And we can't do any row swaps at this point. So what we'll have to do is we will have to rely on division. So this would be row 3 divided by 5, because that's what I'm trying to turn into a 1. And we will replace row 3 with that new result. So it would end up being, let's see here, this new matrix here. From here, then, we want to get the zeros above this last one. And so that requires 2 more row operations. Both of them are going to involve row 3, so we will take row 3 plus row 1 and replace row 1 with this new result, and row 3 plus row 2 and replace row 2 with this new result. Again, we have to figure out what we're multiplying by. When we try to get a 0 up here, we need the opposite of this number added to it, so we'll multiply row 3 by -3. And we will multiply row 3 by +2 when we add it to row 2. And I realized I just made a very large error here. In dividing row 3 by 5, I actually should have divided this number by 5. So that should be a -1. There we go. Now we can continue and get the final matrix after performing these 2 row operations. Here it is in all its glory. You can see that we clearly got the ones on the diagonal. We got the zeros below and above the diagonals, which means then we can go off to our answer. And the answer here, remember we were using x1, x2, and x3 for this example. Our answer would be 9, -7, and -1, right? You can just read right down this column, which is very nice. And again, if you wanted to, you could write this as an ordered pair. Again, it all depends on how you're being asked to give your answer. All right, I've got one more example, and I think it'll be going a lot quicker than this previous 2 examples. Let's get to it. Final example here, we have 3 equations again with 3 unknowns. The first step, of course, is to put the system into an augmented matrix. So I'm going to go ahead and actually give you all a chance. Pause the video, see if you can get a 1 on the diagonal and zeros beneath it, then the next one on the diagonal and zeros above and below, and so on and so on. Go ahead, give it a shot. And I'll be back with some answers in about 5 seconds. Okay, here's everything all the way to completion. We have the matrix. Of course, we have to swap row 1 and row 3 in order to get a 1 on the principal diagonal. And then I perform a couple row operations here to get zeros underneath it. Then, for some reason, we lucked out this time. We ended up with a 1 on the principal diagonal once we did our row operations. So we don't have to worry about getting a 1 on the diagonal in the next column. It's already there. So from there, that means we can jump right into getting the zeros above and below this 1 by these row operations. And then when you do that, you'll notice the bottom row becomes 0, 0, 0, 1. And with that, we can stop, as you can see my big word stop here, and say that the answer is no solution. Because what this bottom row is telling us is that there would be 0x1s plus 0x2s plus 0x3s equals 1. So we're essentially saying 0 equals 1, which is false. So this final one has no solution. And that's it. This is the end of the video, and I very much hope that this video has given you a better understanding of how to solve linear systems with 3 variables and 3 equations much better using Gauss-Jordan elimination. I know I went over 2 different solving techniques. You can pick whichever one you like best. They both work, and I wish everybody luck.